Welcome everyone to our IXPUG webinar. Today's topic is performance optimizations for end-to-end AI pipelines. Our distinguished presenters are Meena Arunachalam, PhD, Principal Engineer, End-to-End AI Performance Architect. Meena is joined by Rishab Sanghavi, Senior Software Engineer. Meena and Rishab are part of the Machine Learning Product Architecture Group at Intel Architecture, Graphics, and Software. Meena, please begin.
Thank you, Shari, and good morning to everyone, and good evening to, depending on the time zones you're in. I want to talk, myself and my teammate, today we are going to be talking about performance optimizations for AI pipelines. And we will hopefully give you enough motivation to go and try out our optimizations and actually use it in your HPC AI development. So let's go to the next foil. So let me start with the outline first. We will begin with motivation for what we mean by end-to-end AI pipelines, and why it's extremely important to think about the entire pipeline, not just the model building or the training portion or the inference portion by itself, standalone, because anything you do either in research and developing as a data scientist or a machine learning engineer or a HPC AI researcher, you pretty much go through every one of these phases and you spend significant amounts of human capital in terms of human cycles, hardware cycles, and software cycles as you think about your problem as a full end-to-end pipeline. So then we will talk about Intel oneAPI AI Analytics Toolkit. This is something you can download today. It is part of the Intel's oneAPI ecosystem. And then we'll show you how to download and how to sort of get all these different optimizations, performance optimizations that are built into these libraries, as well as these familiar APIs and packages that you as an ML engineer or a developer or a data scientist really uses. So the whole idea is to give you near literally without really having to change single line of code, maybe just one line to import those packages, but be able to get the benefits of the ninja coding style of benefits of the lower level libraries. We will touch upon things like oneDAL for data analytics library, oneDNN, which you probably are familiar for deep neural networks, and a host of other libraries that will benefit you throughout these end-to-end pipelines. We'll talk about Intel distribution of Modin. This is a very exciting project. It's only a few years old. It is, think of this as your extremely optimized data ingestion, data pre-processing, data wrangling, all those initial phases that we talk to data scientists who spend a lot of their precious time on. So this is going to make it really go fast. So we'll talk about the Modin's architecture and also give you some motivation with a couple of workloads, namely New York City Taxi Workload, and show you even with within a single node and with our Optane PMEM, you can really run extremely large data sets on Xeons. Followed by that, I'll be talking about machine learning, Intel's extension for Scikit-learn and XGBoost. These two packages are extremely popular and familiar with a lot of the data scientists and ML engineers. So we will talk about how you can use these and somehow get really a significant performance boost. And we'll talk about how we arrive at those optimizations. And then Vishwa will also talk about a few end-to-end workloads, and then end with some auto hyperparameter tuning. And then finally, we'll touch upon ready-made or validated oneAPI, Intel oneAPI containers for some of these workloads that you can go try yourself. Okay, so let's go to the next file. Okay, so here is a pipeline. So what are these? What do we mean by an end-to-end analytics and AI pipeline. So data scientists, ML engineers, deep learning researchers, production deployment engineers create AI pipelines. And they, like I said, they spend a lot of their valuable time. In fact, when we talk to some of these data scientists who do this on a day-to-day basis, they say they spend much of their time on cleaning, data exploration, data wrangling, feature engineering, sometimes as much as 90% in those earlier phases, right? The data loading, ingestion, cleaning the data, feature engineering, ETL, data preprocessing. This is extremely critical in order for us to improve their productivity, which is paramount for anybody who is involved in AI. So you want to be able to quickly manage and run the huge volumes of data, and especially in the high performance computing space, you come across even significant volumes of data, and running through these processes iteratively, because you go through the earlier phases, you build a model, you again go back and then prototype, do many experiments, right? So in order for you to be able to do this in a productive manner, we need three things. We need ease of use. So all the APIs that you're familiar with, we need to support them. Number two, we need to have them extremely performant. It has to be multi-threaded. It has to take advantage of our features on our hardware. And essentially, for you to be able to realize productivity on a day-to-day basis, where you can do fast prototyping and be able to arrive at your solution quickly, the time to solution. And thirdly, you want this to be from generation to generation, as the CPU generations advance, take advantage of our features very quickly, right? And you want them to be scalable, as well as using your familiar APIs. So like I said, the speeding up of every phase is important. So what you will see is the data ETL or pre-processing, the cleaning and wrangling. It's the initial phase, as we are saying, Intel Optimized Modin project with an OmniSci backend. We will show you some of that we'll talk about. And the model building, of course, you can approach it with a classical ML and DL with Scikit-learn, with a Python interface called DAL for Pi, and then XGBoost, which is an extremely popular extreme gradient boosting package, which has won many different competitions, as well as solved many crucial industrial and HPC problems. And then, of course, you have your Intel-optimized Tensorflow, PyTorch, and then low precision optimization tool. All of this is part of the end-to-end AI pipeline and is at your disposal. And ultimately, you also have to worry about how do you potentially deploy this in production and be able to quickly version control and manage all your models. So you may have heard of terms such as the AI tax, hidden technical debt, and others, which is the cost of the other cycles in terms of both hardware, software, as well as human, as well as a solution time that is spent on deploying these AI models in production, keeping them relevant and getting them updated regularly with new data sets, right? So all of this is critical to think about, and the entire pipeline needs to comprehend all that. So like I said, you're going to get the benefits of the huge ninja coding benefits while you're programming at high level languages like Python or any other language, but then you are pretty much getting the oneMKL, oneTBB, DPC++, oneDAL, all those lower level library optimizations very easily by utilizing these APIs. Okay, next file, please. So this, okay, so I like I said, we have been talking to a lot of data scientists and also in production what happens. So this is from one example of a customer, and I just want to show you what it took the customer to go through the pipeline to build a solution, an AI solution, right? So first, they had to start with literally at the very beginning, where you're sourcing the data from, and it can take several months sometimes as the first step, because in this particular case, they decided to go with a deep learning solution. And in order to do that, you need a lot of data, good volume of data, but good, clean, labeled data. And data collection program had to be started. This was for some undersea equipment to look at the potential, corrosion of these parts and be able to predict if a part is, or classify a part if it is corroded, right? And then replace it in a timely basis. So they had to get a lot of different images and then make sure they label it and then classify it and add a label to it, whether it is corroded, what part of it is corroded, etc. The next step is pretty much the whole development cycle, which I'll walk through, and then followed by, once you go through the full development cycle, which is what I'm talking about, the end-to-end AI pipeline, and then you deploy the training model. So, and then you tweak the training model over time with tuned hyperparameters, and over time you update with new data sets. But let's go to what the development cycle is. So notice the total time to solution is what an end user really cares about, right? Because from the moment you get the data to where you're productively deployed a model and be able to get results out of it. So the development cycle includes data preparation, because once the images were given to us, the user had to then label them, like I said, but also potentially create binary masks, because these are going to be used by DNNs, and those were important. And then data augmentation, you scale the data, scale the image, you flip the image, you rotate the image for multiple reasons, which gives you more data volume, but also better results out of your model. And thirdly, this whole process of the data preparation, which is the labeling, loading, augmenting itself, took 50% of the total time to solution. It's hard to believe, but that's what it did. And then the topology experiments, there were 2 deep learning networks that were used, one for localizing with a unit which part of the image is corroded or showing a corroded part, and then followed by a classifier. A ResNet was classifying the whether it was corroded or not. So, and then once you develop the network to your content, and then you basically go tune your hyperparameters in terms of batch sizes, starting weights, learning rate, cost function, etc., right? And then ultimately, now you go deploy it in the real world, and then you inference, in volumes of data. Okay, so and not to mention, you also do documentation of your model. So this is pretty laborious, and in order for you to be productive, you want this whole process to be going smooth with familiar tools and APIs, and ultimately get you to be very productive. Okay, let's go to the next foil. Okay, so here I just want to show you this Intel oneAPI ecosystem. I'm really not going to get into oneAPI because I think there have been talks in the past, but all I want to mention is that the Intel's reference implementation of oneAPI is a set of toolkits, and the Intel oneAPI AI Analytics Toolkit is a very important part, and it pretty much targets all your XPUs. And those are the hardware targets below. And then you have all the various libraries, and then the middleware and frameworks, and then ultimately you build your applications on top of it. So one of the toolkits is the AI toolkit, AI Analytics Toolkit, which is what we will be focusing on today. So if you go to the next foil, we will see that this is the architecture of the oneAPI Analytics. AI Analytics Toolkit. Like I mentioned, we have the deep learning components, we have the machine learning components, we have the data analytics components built on top of the core Python packages, as well as NumPy, SciPy, NumPy, Pandas, DPPY. And at the very low level, you have all the oneMKL, oneDAL, oneDNN, oneCCL libraries as well. So this is what you will get when you go download your oneAPI AI Analytics Toolkit, and you can get to productivity really in a matter of a few minutes. And then we'll talk about subsequent foils, how to download this, and how to install it and how to really get the benefit out of these different tools and essentially use it to power your end-to-end AI pipeline. So I'm going to hand it off to Vrishabh, and then I'll come back to a subsequent foil. Vrishabh?
Hey, thanks, Meena. In order to download the Intel oneAPI Analytics Toolkit, the download link is provided on this slide. So once you click the download link on that landing page, you can click Get It Now and select the operating system and the distro. That will provide a list of installer types and the download instructions, along with the Getting Started guide for that particular installer type. I also have a bunch of links here to the top level Getting Started guide and a few code samples that can be used in order to try out features and functionalities that are included in the Intel oneAPI Analytics Toolkit. The Intel distribution of Modin is a data frame library that wraps Pandas and transparently distributes the data and computation. So it accelerates your existing Pandas workflows with a single line of code change. And the link to the Modin GitHub project is provided down here. Many of you would be familiar with Pandas, which is the go-to library for processing data in Python. It's easy to use and flexible, but it's extremely slow for larger data set, since it executes its functions with a single process and uses a single CPU core at any time. However, the modern machines that data scientists, developers, researchers use these days are multi-core, and the Modin library helps accelerate these Pandas workflows by transparently distributing the data across all those available cores. Only a modification of the import statement is needed, as shown here. Thereafter, users can continue to use their previous Pandas notebooks with those familiar Pandas APIs and experience a considerable speed up from Modin, even on a single machine. Modin also scales well from laptops to workstations to servers, all the way up to the cloud. It is not limited by a single-threaded Python runtime, and it's a multi-threaded implementation providing multi-core parallelism on a single node and multi-node parallelism on a cluster or a cloud. It's also been a very popular project, which was started back in 2018 and has seen around 420,000 downloads. This also underlines how important it has been for data scientists and machine learning researchers as they grapple with these data exploration problems on huge volumes of data. Here's the architectured and layered API view of Modin. So you can see there are three main layers here: the user level API, the system level API, and the middleware. The user level, which has the user facing APIs, comprise of the Pandas APIs, their support for SQL, and domain specific languages like IBIS. These APIs are fed to the query compiler APIs, which is the starting point for the system level APIs. So the query compiler takes API calls from the user level and translates them to direct acyclic graphs of query execution represented in the data frame algebra. Then there are two more APIs representing storage and execution, to which these DAGs map to in order to be executed. The middleware layer that you see here has various backend supports and executors like Ray, Dask, and MPI. OmniSci is the backend subsystem and engine that compiles these queries and runs it on the Ray worker, which then runs on multi-core or distributed mode. So that's a broad overview of the Modin layered architecture. I'll now present the speed up achieved through Modin over Pandas using a workload called New York City Taxi. The dataset used for this workload has up to 1.1 billion rows, with each row corresponding to individual taxi trips in the city of New York from January 2009 to June 2015. And it contains demographic information of customers and vendors, as well as information about the trip, like the pickup and drop-off location, the time of the trip duration, etc. So I have a few snippets of the workload code here. The workload consists of a data ingestion section that you see here, where it reads the CSV dataset and creates a data frame from it. It's then followed up by 4 different queries that are typical and representative of data frame queries that you see in a typical AI end-to-end workload. So for example, the query 1 here, it computes the group size based on the cab type, which is the green or the yellow cab in this case. Query 2 does an aggregate group by over the number of passengers per trip. Query 3 does an aggregate group by over the number of passengers per trip as well as their pickup years. And query 4 casts the trip distance field as int64, computes the group size over the passenger count, pickup date, and trip distance, resets the index and sorts it according to the pickup time. So these 4 queries are actually very typical and illustrative of the data frame queries that are commonly seen in end-to-end AI applications. The following slide here shows the speedup that is achieved by using Modin compared to Pandas for read CSV and for processing the 4 queries that I detailed on the previous slide. The chart on the left is for the 20 million rows, while chart to the right is for 1.1 billion rows in the input data set. The green bars show performance using the Pandas library, and the blue bars show performance with Modin relative to Pandas. So a speed of about 10x is seen for the read CSV function on the small and the large data set, and speedups ranging from 10x all the way up to 90x is seen for individual queries. This speedup is achieved as a result of the multi-threaded parallel implementation of Modin over the single-threaded Pandas. And it's also easy to see that Modin seamlessly supports data frame sizes from a few megabytes to more than terabyte sizes. This 1.1 billion run that is carried out here is using the Intel Optane persistent memory modules, also called DCP-MM. They provide comparable performance and much larger capacity than traditional DRAMs. Omnisite DB, which is the backend engine that we have in Modin, can take advantage of DCP-MM capacity to run these huge workloads that are not able to run on traditional DRAMs. And it does so without having to make any source or binary code changes. And now I'll pass it on to Meena for Scikit-learn and XGBoost.
Okay, thank you, Vrishabh. So now let's jump into the Intel extension for Scikit-learn. Like I said, this is a very popular package that has many different estimator models, transformers, data preparation, and different algorithms that it covers. And then we'll also focus on the extreme gradient boosting package, which is a standalone package and extremely popular these days, both for Kaggle and for other applications. So we have a link here to the oneDAL project that is open source. You can definitely take a look at it. And there's also, I want to bring your attention to this medium.com website where we post a lot of very interesting blogs of various Intel analytics software that you might find useful. Okay, let's go to the next slide. So here is your oneAPI data analytics library. Architectural picture or building blocks that you can see that form the, basically the oneDAL library, right? So we have both a Python binding and as well as Java Scala binding as well as C++. You can directly program in DPC++ or C++ as well. And so let's take, for example, the Intel extension of Scikit-learn. So what you would essentially do is you would pretty much invoke the Python interface, and then it will eventually connect with the oneDAL interface, which is the DAL for Pi interface. And then underneath, you will pretty much get the algorithms that are either in the batch mode, streaming mode, or distributed mode based on the particular API you invoke, and then target the appropriate backend that you are using, the CPU or GPU backends, and then ultimately invoke the optimized kernels on that particular hardware. So it's extremely straightforward. There's nothing you really need to do other than pretty much importing this. So there are multiple ways to do it. You can either import this package and then pretty much use the same APIs, or you can also patch it at command line. the thing I want to sort of draw your attention to is that oneDAL uses all the capabilities of Intel hardware, whether it is vectorization, beta cache reuse, and so on. And while the higher level programmer enjoys the benefits of all these low level optimizations. And the Spark, Apache Spark optimizations with the MLlib API, and then using the oneDAL solvers are also in progress. And then with respect to XGBoost, we pretty much upstream the optimizations we do into the main line of XGBoost. But in addition, we also have an interface to DAL for Pi, which will sort of, once you build the model, train it with XGBoost, you can do even faster inference if you use the DAL for Pi optimization. So whether it is pre-processing, transformation, analysis, modeling, validation, and decision-making, all stages of the data analytics, the various blocks that are supported by Scikit-learn, you're going to benefit from oneDAL. And this is also part of, like I said, the oneAPI Analytics Toolkit, as well as the Intel distribution of Python. So next file, please. Okay, so I kind of want to draw your attention to what makes oneDAL faster, right? So let us say we both start with the C++ baseline, the end user as well as the oneDAL code, but then you essentially, underneath it calls the oneMKL library for all the BLAS functions, and which are extremely optimized and gets the best performance on the particular Xeon CPU generation that you're using. I think most of you are probably familiar with oneMKL and you're probably already using it. Second step is it adds very good threading wherever possible, wherever the algorithm allows, and essentially uses the many core systems to achieve efficient scalability as you're going from generation to generation with increasing numbers of cores, right? Whether it is the target library is a client version or a very high-end server part, irrespectively, automatically it figures out the amount of scaling available and accordingly optimizes the library. Thirdly, vectorization, which is very critical as you go from SSE to AVX2 to AVX512 and so on. This generational advances we see in vector instructions, these are also either enabled them by compiler options or intrinsics and are taken advantage by these ML library implementations. And we have the oneDAL, we also do the memory optimizations, whether it is, accessing memory minimally or better cache reuse, software memory prefetching where possible. And these kinds of optimizations are also very much in tune to get the best performance out of the hardware. And then finally, before you even the hardware comes out into the world, we start working on oneDAL alongside hardware as the hardware features are being designed. So we optimize for the new instruction set architecture, new hardware features that are planned for. So as soon as the hardware comes, you can really get to production very quickly. And then we're also doing distributed algorithms so that for scale out, it is pretty seamless and you can use oneDAL. Okay, let's go to the next file and then show how easy it is to use Scikit-learn, Intel extension of Scikit-learn. So on the left, you see your common Scikit-learn. Here is a support vector machine, a classifier that's happening. And you are pretty much doing both the fit, the training, as well as predict inference. And then in the middle, literally, I can do two things. One, I can do import DAL for Pi as D for P, and then do a patch upfront, and that's all you need to do. And nothing in your program needs to change. All the APIs, everything stay the same. That's one option. The other option is you could also patch it on command line. This is available through pip install, and you can very easily install DAL for Pi. The key I want to draw to you is this is Scikit-learn, exactly Scikit-learn, not Scikit-learn like. And the other important part, which is very crucial for a lot of HPC and a lot of other applications as well, is the Scikit-learn numerical conformance. So the Scikit-learn consortium has a certain conformance testing, and that is expected of each algorithm's implementation, mathematical equivalence. This is continuously vetted and tested by as we do continuous integration. This is continuously tested, and only then we accept those changes into DAL for Pi and oneDAL. So so you can pretty much very easily literally drop in replacement for your API calls. Okay, so let's look at some performance numbers next. So here we picked a few popular algorithms with different numbers of features and different sample sizes, and looked at both predict as well as fit. And you can see these are the speedups. Mind you, anywhere from 3.6x to 221x speed up improvement in performance of the unoptimized or the stock scikit-learn or the original scikit-learn versus the oneDAL powered scikit-learn. And again, I want to bring to your attention that this was on Intel Xeon Platinum SKU, which is a Cascade Lake part with 28 cores per socket. And you will pretty much see this kind of scale of improvement on any Xeon, but the most important thing is its drop-in replacement, and it is Scikit-learn APIs, and it has the Scikit-learn conformance, the numerical and mathematical conformance as well. Now, okay, this is great. So you might say, okay, Scikit-learn needed to be optimized, you did that. But how do we compare against competition, right? So let's look at a couple of data points here, actually more than a couple, on a variety of algorithms again, on different shapes and sizes. So the yellow line is at the 1.0, which is the Xeon baseline with the Intel extension for Scikit-learn accelerated by oneDAL. And anything below that means that the competitor part is underperforming. So pretty much across all these algorithms, Xeon 8280 Cascade Lake SKU with 28 cores per socket is outperforming. So you can see that the blue line is the IDP Scikit-learn on AMD Rome 7742, and the green bar is the Rapids QML.15 on an NVIDIA V100. And there's a much more deeper blog in the Medium website I talked about. You can go look at the more details. And more importantly, I want to draw your attention to the Scikit-learn bench that is out there. You can pretty much download, it's open source. You can go to the GitHub site, which is also listed in the blog, and you can pretty much download it and test it and run it for yourself. And we would love to get your feedback, and then let us know what are the things that you like about it and what additional features you would like to see, right? And there is a roadmap, and which we have added in the backup, what algorithms are covered right now and what are planned for, and so on. Okay, so let's now go to the next foil, which is talking about the extreme gradient boosting, machine algorithms, the package that by standalone package. So in a matter of if you look at on different data sets that we looked at the XGBoost algorithm, and you are seeing acceleration versus the baseline being XGBoost version 0.81 on a Cascade Lake 8280 CPU. And then if you use that as a baseline over a matter of a few quarters, we got to XGBoost 1.3, we upstream the changes, and you can see that the speed up substantially improved. Right? And just to show you on the right, XGBoost 1.2 versus version 1.3, the prediction speed up went up on Intel CPU. You can see on different data sets. Just again, I'll talk in a minute what are the different optimizations we did. One of the things in this particular case was reduction in the memory consumption, right? So we reduced it approximately 2x, a reduction in the the memory consumption on the pull request 5334, and you can see these benefits. So if you go to the next file, you will see that what it took to go from XGBoost version 0.81 to 1.3. So I'll just give you some examples, like it's a pseudocode on the left for the version 0.81, and then for the 1.3 on the right. Memory prefetching, right? These are, in these cases, these are building decision trees, highly irregular memory access. So memory prefetchers were inserted to mitigate and basically reduce the latency to memory. Nested parallelism by the decision tree nodes. So there's a parallel for, and then you're able to go at it across the different threads. We used lower precision for the histogram building, and if you noticed, we went with integer int 8 instead of int 32. That helped a lot. Advanced parallelisms for the sample partition function, and which reduced the sequencing loops. And all this without even yet going to the SIMD instructions, full blast with AVX 512. So that is what is planned in the next step. So the beauty of this is there's a lot of optimizations that were done to the code, and it will be continuously optimized and released both in the mainstream as well as in the AI Analytics Toolkit, and the user can seamlessly get the benefits of these optimizations. Okay, I'm going to hand it to Rishabh now to go through the end-to-end machine learning workloads, where we'll walk through a few use cases, sort of put together all the different optimizations you saw from Modin, from Scikit-learn, from XGBoost on a couple of workloads.
Yeah, so I'll go over a couple of end-to-end AI use cases and pipelines and demonstrate the performance speedup that we achieved by using the Intel optimized AI libraries that we talked about previously, as well as some performance improvement using hyperparameter tuning. So by end-to-end workload, it means a code that encompasses the entire machine learning pipeline, from ingesting the input data set into data frames, manipulating, transforming, processing it, and using it to train the model, make predictions, and calculate the accuracy of those predictions. So here I'll present two such end-to-end workloads, Census and Plastic, as examples to demonstrate the efficient AI pipelines and showcase possible speedup from the Intel optimized libraries and hyperparameter tuning. So the Census workload trains a rich regression-based model using the US Census data from the years 1970 to 2010. And it predicts the education level of people based on their income, age, and gender. I'll go into the flow and components in some detail in the next slide. The out-of-box unoptimized run would use the Pandas library for ingesting the CSV dataset and to perform ETL operations, and uses stock Scikit-learn library to train the model and run inference. With the optimized software stack, it uses Modin with OmniSci backend for read CSV and ETL operations, and uses Scikit-learn accelerated by oneDAL for training and inference. Further performance improvement can be obtained by tuning the hyperparameters using SigOpt or any such similar tuning softwares. I'll go into some details regarding SigOpt in the forthcoming slides. Plastic is the other workload that I'd like to discuss here. So Plastic is an open data challenge on Kaggle with the aim to classify objects in the night sky with varying degrees of brightness, and it uses simulated astronomical time series data. So this challenge on Kaggle is actually in preparation for observations that are to come from the Large Synoptic Survey Telescope, which is currently being set up in northern Chile. So the idea here is to classify each object into one of the 14 astronomical filters. So the workload is basically a classification problem. The out-of-box unoptimized run uses Pandas for read CSV and ETL operations, just like Census, and XGBoost for training, cross-validation, and inference. While the optimized software stack that we discussed previously in the presentation would use Modin with OmniSci backend for read CSV and ETL, and it uses XGBoost for machine learning operations. And just like Census, further performance improvement can be obtained by hyperparameter tuning. So here's the flow chart that shows the code path for the census workload. I won't go into a lot of detail on this slide, but want to emphasize the fact that a typical end-to-end workload has three broad components that you see here in these three different boxes. In the read CSV section, it ingests the CSV file into a data frame, and you can see the shape and size of the data frame at each stage in the corresponding boxes on the rear. For the ETL operations, it drops non-essential columns, removes rows with erroneous data, fills NA fields with -1, does type conversion on some columns as well as arithmetic operations, and creates a feature set and its subsequent output set at the end. It then splits the data set 10:1 in order to create a training set that is used to build the model and a test set that is used to make predictions. This particular process is repeated 50 times in order to randomize the split and remove any potential bias that may have crept in order to avoid overfitting. Finally, in the machine learning section, we use the training set to build a ridge regression based model and use that model over the test set to make predictions. And lastly, the accuracy of the prediction is calculated using the mean squared error. So that's the overall flow of the end-to-end census workload. Plastic has a very similar code flow to Census as well and has the same three broad components. It has a separate training and test set, and the test set is unclassified. So that is what is used to run on the trained model. The read CSV section here reads all four sets of data and ingests them into data frames. So this code has time series and its corresponding metadata, which is why you see these multiple blocks here that creates multiple data frames. In the ETL portion, both the training and the test sets go through arithmetic operations, group by aggregation, drop columns, merge operations, in order to prepare these data frames for the machine learning operations that are to follow. And finally, in the machine learning section, the NumPy array is loaded into dmatrix objects, and the histogram tree method is used to build the XGBoost model over the training set. This trained model is run on the cross-validation set and the accuracy is calculated. And lastly, this model is run on the test set, which is unclassified, in order to classify these objects into one of the 14 astronomical categories. So this slide shows the performance of the census and plastic workloads that I just mentioned. The pie charts on the top shows the phase-wise breakdown and the percentage of time spent in each of the phases that I described on the previous couple of slides. The bar charts below show the relative performance and the subsequent speedups that are obtained using the optimized software stack, which is shown in this orange color, over the unoptimized software, which is shown in yellow, in each of these phases. So higher is better in case of these bar charts. A massive 10x end-to-end speedup is achieved in Census, and 18x end-to-end speedup is seen in Plastic by using the optimized software. All of the speedup is seen without making any API change by merely using Modin for read CSV and ETL operations, and Scikit-learn accelerated by oneDAL for the machine learning portion on the Census workload. We see these significant improvements to the tune of 7x in read CSV, 4x in ETL, 9x in train test split, and 59x in machine learning time. Similarly, on Plastic, we see a massive 69x improvement in read CSV, 21x in ETL. So all of this performance improvement showcases the power of optimizations on the Xeon platform that is unlocked through parallelization, vectorization, core scaling, better memory layouts, cache reuse, and memory bandwidth optimizations, all of which are brought in through these libraries that we talked about. We can further improve end-to-end workload performance by tuning the hyperparameters that are there in the machine learning models. One such extremely efficient and quick way to do so is using SigOpt. So SigOpt is a model development platform that makes it easy to track our runs, visualize training, and scale hyperparameter optimizations. It works for any type of model built with any library and on any sort of infrastructure. It's basically a black box optimization that efficiently optimizes any machine learning or deep learning model. So in the next couple of slides, I'll go over an example on how we set up SigOpt hyperparameter optimization for the census and plastic workloads, and what performance improvement it delivered over the search space that was defined. So SigOpt's optimization feature helps find the values for parameters of the model and provides the global optima for the defined metric. So for example, it can be used to minimize the runtime metric. We need to write a Python code, a small snippet of which is shown here, to fit our code within the SigOpt framework, wherein the experiment needs to be created, a model needs to be parameterized, and finally the optimization loop needs to be run. It runs these experiments on the hyperparameter search space and the metrics that are needed to be optimized. This experiment must have a name and at least one parameter and the metric that it is trying to optimize. So in the code snippet that you see here, the experiment name is XGBoost. The metric that it is trying to optimize is the accuracy and the timing. And the parameters are defined using a list of dictionary with a minimum and maximum range for those parameters. That's what you see here in this block. The observation budget is the minimum number of observations that will be reported in order to seek the global maximum or minimum of the objective function. And we've seen that convergence mostly occurs when this budget is set to 10 or 20 times the number of parameters in the experiment. Here is the list of hyperparameters that are exposed by the two algorithms. These parameters are used to optimize the accuracy and timing metrics for the workloads that I had previously mentioned. So for the ridge regression algorithm, which is basically the census workload, alpha is the normalization parameter, and n-rounds is the number of times train test split is performed in order to randomize the training and test set in order to avoid overfitting. And for XGBoost, which is the plastic workload, we use the histogram tree method and we specify a number of minimum and maximum range for all of these hyperparameters, like the number of parallel threads to run XGBoost, number of trees, number of discrete bins to bucket into continuous features, maximum depth for the tree, learning rate, L1 and L2 regularization terms, and so on. So this is the broad range of hyperparameters that we had put in. And this is the previous set of end-to-end workload performance graphs that I had shown for census and plastic. And now I'm showing the additional performance improvement that is obtained from tuning the respective hyperparameters using the SigOpt tool within these experiments that we had defined. So the brown bars that you see here show the speed up in the machine learning portion due to the hyperparameter tuning. Consequently, we see a further 2.3x performance improvement for census by tuning these hyperparameters, and a further 1.5x performance improvement for plastic with the hyperparameter tuning. So all of these steps that I showed in the previous few slides performed over a typical end-to-end AI pipeline shows the massive performance improvement that can be achieved on an AI workload using a variety of Intel optimized software packages, libraries, and tools that we discussed earlier in the presentation. And I'll pass it back to Meena for the Intel oneAPI containers.
Thank you, Rishabh. Okay, so I wanted to close this with hopefully we have given you a taste of the different software optimizations we have done and motivated you to try it out on some of your own problems. But also want to show you these oneAPI, Intel oneAPI containers in the container portal, software.intel.com/containers. What you will find there is optimized, validated, deployable AI containers. Either you can get the Docker containers themselves with Intel software stack, or you can get Kubernetes orchestrations, Helm charts, AI models and pipelines, or you can also get some specific solutions or problems that a particular container or solution implemented and presented in a container. So as well as model zoo with pre-trained weights ready for training and inference. So these are just some of the models that we have today listed below, and then more are being added actively. So I encourage you to go and check out this website. In addition, ML models are also getting added, and we will be also providing these workloads we talked about over there, Census and Plastic. And then, like I said, you can also try the Scikit-learn bench, and then try it for yourself if you're interested in the ML algos. So with that, I just want to go to the next foil, which kind of shows you the configuration details of the different runs and the performance data that we talked about. So followed by in the backup, we have some of the different oneDAL algorithms, and then that are planned for and what we have available both in the batch mode, streaming mode, and then the distributed mode. So thank you so much for your time. And Shari, do we have any time for questions, or if there are any questions?
Thank you, Meena and Rishabh, for the presentation. I think we have some time. We can go over some of the questions. Please, you can raise your hand, or and I can unmute you to ask your questions, or you can actually even type out your questions in the chat window, and I can take the questions from there. So I tried to answer a couple of questions, Meena, already. These are some generic ones. I am not sure, but I will read them out, and you or Rishabh can take it. So one of them is, can you talk about SigOpt? What is the value prop? All the cloud platforms already have hyperparameter settings. So I guess the question is, what are the benefits of using SigOpt?
Sure, SigOpt, right? Okay, yeah, SigOpt. I can take that. So it is. You're right. I mean, there are a lot of different solutions offered on cloud service providers, right? But this one is something that is integrated with our libraries, as well as plans for including hardware tuning as well as software tuning, right? Together as one integrated end-to-end deployment solution. So the SigOpt development is part of our team as well, our bigger organization, and a lot of exciting things are planned as well. So yeah, I hope that answers your question.
Okay, and I think there were some questions around the one MKL to one DNN is not applied to each of your development phases, right? It's just the oneAPI libraries. I sort of clarified that these libraries are part of the oneAPI spec.
Correct.
Yeah. And is there anything else you would want to add?
The thing I want to mention is that if you go to the oneAPI, if you go to the foil number, Rishabh, on foil number 7, I think, it will, or 7 or 8, it'll show you the modes on how you can sort of download this. So it comes as oneAPI AI Analytics Toolkit. You'll pretty much get all the pieces you need for doing any AI analytics or workflow, right? And you can get it as a Docker container or a Yum or apt, or I think the next foil probably, right? And there are modes of getting it. So let's say you decide I only want to do ML or DL, you can appropriately also decide to download individual components if you choose to, right? So that's kind of the plan.
Okay, I think those were the questions specific to the presentation. I think I've answered all of George's questions of the generic ones. Okay, that's about all we have in the chat box. Are there any other questions? You can raise your hand, and we are virtual hand, and I can unmute you if you have any questions. Let's give it a minute if anyone else has any questions. I guess not. Okay, thanks again, Meena and Rishabh, for giving us this presentation. I hope all the attendees found it useful. You will find a recording of today's webinar and the content, the slides, online on ixpug.org under the webinar section. We'll also send out an announcement about that. Thank you everyone for attending.
Thank you so much.
Yeah.
Thank you for the opportunity, Nalini and Shari. And yeah, we will post the files. We'll send it to you, right? And then you'll post the files.
Yes. Thank you. Thank you so much.
Okay. Thanks so much.
Thank you.
Bye,
Thanks,
everyone.
everyone.